Hello everyone. So today I'll be trying to explain SWATH-MS, which is a new technique of tandem MS, and this I am going to explain in a very simple way or in a very understandable way. For this, the prerequisite understanding you need to have is of tandem MS, basic tandem MS. Now this is a pictorial representation of tandem MS where first of all you have the liquid chromatography which separates your analyte mixture, and here you can use different types of chromatographic columns such as Helic or RP, or there are different columns from different vendors that you can use to do the separation. The next step is the ionization, where you ionize the analytes which are coming from the column, and ESI being the most popular one among biologists. This is a soft ionization technique, as in it does not uh, cause harm to the analyte molecules themselves. Often proteins are very fragile in case of ionization, so you ionize the analytes, and then the next part is the first mass analyzer. Over here we can see Q1, and Q1 is representing a quadrupole mass analyzer. There are several videos on YouTube, you can check them out to understand what a quadrupole is. There are other mass analyzers as well, such as TOF or time of flight mass analyzer. This here is getting the data for the MS1 level. So at a particular RT, it will gather the data of the peaks or the M by Z of the peaks and get the intensities of those peaks. Now, what I want to point out here is this is MS1 level data, or this is only non-fragmented data. So next, in tandem MS, the next step is the fragmentation of the peaks. So we fragment for one peak. I'll just take example of this peak. Let's call this peak X. So we will take X, and then we will suppose this is a molecule somewhat like this, uh, CHH, and there's some CH3, there's a benzene ring. So we will fragment this. By fragmentation, what I mean is, let me just erase this. By fragmentation, we will break the bonds over here, and we will also break a bond here or break a bond here. It is all depending on the molecule itself, and then after fragmentation, it will give me three peaks, right? If I analyze the fragments, and these three peaks will be measured in the second mass analyzer. This is the collision cell here. This is actually where the fragmentation process is happening, and after this we can use the detector and store the peak information. This is the MS2 information digitally for our analysis. This is the basic tandem MS that I wanted to introduce you to. Now, coming to SWATH-MS, SWATH-MS is a little bit different in the way that it is a data independent acquisition technique, DIA. It is also called DIA technique. Now, what DIA technique basically is it does not depend on the underlying data or the underlying analyte molecules that you are using. So the steps in SWATH-MS is, again I am considering it a single RT. So you are getting several analyte molecules which are eluting from the column one by one. Now I will just select at a particular RT. Let's just select RT 20 minutes. Okay, so at RT 20 minutes and 15 seconds, to be very specific. Now at this RT, suppose we are getting 1, 2, 3, 4, 5. 5 peaks at MS1. Again, this is the intensity and this is the M by Z. Okay, now what happens is, first of all, we do a MS1 level scan. So we get this data, and we store this data. After that, SWATH-MS, this is the specific thing about SWATH-MS, it starts selecting windows. By windows, what I mean is it will select a M by Z range. So for example, if you specify in the program or the software of the machine that you want a 50 M by Z fixed precursor window at the in the mass range of 70 to 1200, so it will start the windows from 70 to 120. This is a 50 mz window. Next, this will be the first window. This second window will be 120 to 170 m by z. This is again a 50 mz window, and so on and so forth. 70 to 120, 120 to 170. The next one would be 170 to 220. Again 50 mz. There are other techniques with which you can select a um, variable window size, but that is out of scope for now. Now after you select a window, within that window, whatever precursor ion falls, it will take all of them and it will get the fragmentation data. Now if you understand this again, if I try to explain this once more, you are selecting windows and then windows of precursor ions and then fragmenting them together. Now this all happens within a very small amount of time, like 3 seconds for one cycle. And by cycle I mean at a particular RT it takes only 3 seconds to do the whole MS1 scan plus the n number of MS2 scans, the n being the number of windows that is being specified. Now for 70 to 1200 mz, the number of windows will depend on the window size. So if it is 50 window size, 50 fixed, then it will be 1200 minus 70 divided by 50 windows. So that is, I don't know, you can calculate that on your own. So all of this happens in a very small amount of time. This is 3 seconds for this particular one. Now okay, the reason the SWATH-MS is known as the DIM method is because over here you are not depending on the data. You have a digital record or every fragmentation or a fragmentation information of every precursor ions regardless of what those precursor ions are. So this is a DIM method. Now moving on to the next slide. So over here you can see, so this picture is from the SWATH-MS paper. You can find it in the journal Molecular Systems Biology. This was the original paper. I'll leave a link. Now over here as an example I'm showing. So here you can see that they have selected the MZ range of 400 to 1200 and they are doing a MS1 scan here, one single MS1 scan. So you get everything and then every precursor ions. There are a lot of precursor ions, and then again one more thing, this is at a particular RT. This is at a very particular RT and after every 3 seconds this will change. So you get the precursor ion scan and then over here they have selected 32 windows, and so this example here is showing the window of 925 to 950, so their window size is 25 mz. and in this window they have three precursor ions, 1, 2 and 3, over here depicted as blue, red and green, and they have taken those three precursor ions and then fragmented them. Now this is the fragmentation information of those three precursor ions, and as you can see, this is a chimeric spectra. Chimeric spectra is something where you have the fragmentation information of more than one precursor ion. So here the green, the blue and the red fragments are mixed together. So this is known as a chimeric spectra. This is again a important computational problem, how to identify the precursor ions using the chimeric spectra. This needs something called deconvolution, but that is again out of scope for now. Now moving to the next slide, I have annotated a few things over here to explain this a little better. So over there you can see that they have a cycle time of 3.3 seconds, and the scan time of ms1 is 100 milliseconds. Again, the scan time of ms2 for each window is 100 milliseconds, and there are 32 windows, so that counts to 3.2 seconds for ms2 scans and 100 milliseconds for ms1 scan, so that is 3.3 seconds. Again, you can see over here this is 3.3 seconds. So yeah, now there are small questions. There might be some small questions in your mind, that how are there higher sized fragments than the precursor ions? Since you were selecting a maximum of 950, how is there a peak at 1000, 1200 or something? Now this has to do something with the m by z, since the z is the charge. Maybe a precursor of higher mz had a charge of 2, so it jumped here in this window, but then after the collation cell step, the fragments did not have a z of 2 anymore, and they had a mass of higher than the precursor ions. So this is something that might have happened in this case. And okay, so that is it. I hope you understood whatever I explained to you, and I hope this was helpful. I think this has become very long, and I'll end this video here. Thank you for watching.